Hey everyone. In today's video, we're talking about retaining walls, those essential structures that you've probably seen along highways, holding back slopes, or even around basements in cities. Retaining walls are designed to stabilize the ground and keep soil in place, especially in areas with uneven terrain. By the end of this video, you'll have a solid understanding of what retaining walls are, the key components that make them work, and the forces they're built to handle. So, let's get started. Let's start by defining what a retaining wall is. Essentially, a retaining wall is a structure that holds back soil, allowing engineers to create stable ground levels where natural slopes would otherwise exist. These walls are used in various applications, from creating space for roads and buildings to landscaping and flood control. There are different types of retaining walls, each tailored to specific conditions. For example, a gravity wall relies entirely on its own weight to resist the pressure from the soil. On the other hand, a cantilever wall uses reinforced concrete and a slab foundation to counteract the forces acting on it. Counterfort walls are similar to cantilever walls but include additional support for handling larger loads. Mechanically stabilized earth walls, or MSE walls, use soil reinforcement techniques to increase stability. Each type has its own set of applications and design challenges, which we'll explore in more detail in later discussions. Now that we know the types of retaining walls, let's take a closer look at their components. A retaining wall has three main parts: the stem, the base slab, and in some cases, a shear key. The stem is the vertical part of the wall that directly holds back the soil. It is typically the most visible part of the structure. Below the stem is the base slab, which provides stability and prevents the wall from tipping over or sliding. The base slab has two distinct sections, the heel and the toe. The heel is the portion that extends under the soil being retained, while the toe is the part that projects on the opposite side for additional support. In some designs, a shear key is included below the base slab. This projection increases the wall's resistance to sliding by engaging more of the underlying soil. In addition to these structural components, drainage features like weep holes or perforated pipes are often added to manage water pressure behind the wall. Some walls also include a coping or parapet at the top for aesthetics or additional safety. Understanding the components is just the beginning. Now let's talk about why proper design is so important. Retaining walls are subjected to significant forces, and failure to design them correctly can lead to catastrophic consequences, such as soil erosion, property damage, or even loss of life. A well-designed retaining wall ensures stability and safety while being cost-effective. Proper design also minimizes maintenance requirements over the structure's lifetime. Failures such as sliding, overturning, or excessive settlement can often be traced back to poor design practices or a lack of understanding of the forces at play. This brings us to the next topic, the forces acting on retaining walls. A retaining wall must resist several forces to remain stable. The primary force is lateral earth pressure, which comes from the soil behind the wall. This pressure can vary depending on the type of soil, its moisture content, and how it's compacted. In addition to earth pressure, retaining walls often experience surcharge loads, which are additional forces from structures or vehicles located near the wall. Water pressure is another critical factor, especially in poorly drained soils, where water can accumulate behind the wall and exert significant force. In regions prone to earthquakes, seismic forces must also be considered, adding further complexity to the design process. Now that we've identified the forces acting on retaining walls, let's discuss the principles behind their design. A retaining wall must satisfy two main criteria: stability and structural integrity. For stability, the wall must resist sliding, overturning, and bearing capacity failure. Each of these checks ensures that the wall won't shift, tip over, or sink under its own weight and the forces acting on it. For structural integrity, the wall must be reinforced adequately to handle bending and shear stresses while remaining serviceable. This means avoiding excessive deformation or cracking over time. These criteria form the foundation of retaining wall design, guiding engineers in creating structures that are both safe and efficient. Of course, no discussion on retaining wall design would be complete without touching on the relevant codes and standards. The National Structural Code of the Philippines, or NSCP, provides important provisions related to concrete design and geotechnical considerations, which are critical aspects of retaining wall design. Additionally, modern tools and software have made analysis and design much more efficient. While general-purpose software like StatPro and ETABS are widely used for structural analysis, specialized programs such as ASDIP and Geo5 are tailored explicitly for retaining wall design and geotechnical applications. These tools are among the options available at the time of this recording. In this lecture, we've introduced retaining walls, their components, and the forces they need to resist, along with the principles behind their design. These foundational concepts will set the stage for our next discussion, where we'll start diving into the calculations and practical considerations involved in designing retaining walls. Thank you, and I'm looking forward to seeing your insights and questions.